So thank you very much, everybody, for coming here for this very special event. My name is Stefano Marchidis. I'm a professor here on computer science, working on high-performance computing. And it's really an honor and a pleasure to have Professor Malony here today. So, we share, the same area of research, and this and digital future allow us to strengthen this collaboration. A few words about Alan. So, Professor Alan Malony is a professor in the Department of Computer Science at the University of Oregon, and he's also the director of the Oregon Advanced Computing Institute for Science and Society. He graduated with a Ph.D. degree from the University of Illinois, Urbana-Champaign, and received a number of awards and funding from NSF, the National Science Foundation, as a Young Investigator Award in 1994. He also was the Fulbright Research Scholar to the Netherlands, to the Austria, and he received the Alexander von Humboldt Research Award for the Senior U.S. Scientist in 2002. In 2016, Professor Malony was named the Fulbright-Toqueville Distinguished Chair by the Fulbright Commission Franco-Americaine in France, and he was also selected as the Fulbright-Nokia Distinguished Chair in Information and Communication Technology from the Fulbright Finland Foundation in 2022. Professor Malony has a quite large number of research interests in the area of parallel computing, HPC, and especially on performance monitoring and analysis. And we'll talk a little bit more about the science aspect. So thank you very much for being here with us today. Looking forward to your
great. Thanks, Stefano. I want to start off by just thanking Digital Futures for selecting me as a scholar in residence to be here. I'll be here until the end of January. So if there's any interest in talking after today, I'd be happy to do so. Thanks, Stefano. I'm gonna talk about perspectives, as you see here, on supercomputing, past, present, and future. Stefano covered my bio, so I don't have to do that anymore. Just to say, I'm also a CEO and director of a company called Paratools, as you see here. Tell you a little bit about where I come from. I'm from the state of Oregon, which is in the United States in the Pacific Northwest. It's a very beautiful place. As you see here, different areas geographically within the state. There's some really distinguished features, like in particular, this is called Crater Lake. It's essentially a lake that was formed when a mountaintop blew up about 30,000 years ago, and it's the deepest freshwater lake in the United States. And there's other things. We have mountains, we have coasts, we have a variety of things. My wife, in fact, is going to be at this jazz party happening this weekend with her 87-year-old dad. So I'm hoping that ends up going well. Okay, that's where I'm from. What I want to do today in the seminar is essentially give you, when I say perspectives, really what it is perspectives on what has motivated me, in my career from a research point of view. So what we're going to cover is going to start from the beginning, computability and complexity. I'm going to talk about performance in relation to parallelism, tell you about supercomputing, and then tell you about the work that we do in parallel performance research. Finish up with some future directions and some takeaway thoughts. And for those in attendance here in person, there'll be a special surprise at the end. So stay around for that. I'm going to start at the beginning. And the beginning is with Alan Turing. Alan Turing was someone who lived at a time where mathematics was ruling the day, and problems in mathematics were being proposed by David Hilbert, in particular ones that had to do with issues of whether mathematics is decidable. This problem was the Hilbert's 10th problem, and the general form of that, as you see here, is to have a definite, generally applicable prescription that is used to decide on a particular problem. A particular problem in this case was a mathematics problem. Now, what does that mean? A definitely general applicable prescription is essentially an effective method, some method by which you can, through a sequence of finite steps, address a problem. In this case, it had to do with decidability. Very interestingly, two people, Alonzo Church and Alan Turing, in 1936, actually solved this problem together. And Church's solution was based upon lambda calculus. Turing's solution was based upon a Turing machine, which is essentially a hypothetical computer system. They together posed the Church-Turing thesis, which essentially states that a Turing machine, this abstract computational model, is able to solve problems that are computable. That is, what's computable? It is a Turing machine. What problems are computable? Well, it's those that can be solved by a Turing machine. Interestingly, not all problems are computable. This is something that is a part of the theory around Turing machines. Now, a Turing machine is a hypothetical model, but the way that Turing talked about it is as if it was something that could be done by a person, which he called a computer, someone who was a computer, following a sequence of steps. So effectively, he described how you could take this theoretical model and build a machine to process deterministic rules, which we now know by the name of algorithms. So why am I telling you about this? Well, interestingly enough, Turing machines have a foundation of computability. That is, they are a computational model, but from that model, you can talk about things having to do with the power of computing. Computational power has to do with what can be computed, and what can be computed is what we can express in the form of algorithms that would run on a Turing machine. What does this mean? Well, it means that Turing machines are as powerful as any computer that's in existence today. Computability is not the same as complexity. You know, a problem just needs an algorithm to be computable. But when we talk about complexity, we're talking about how hard it is to solve a problem. Complexity theory is telling us how to talk about this. You know, what are the metrics with respect to that difficulty of solving the problem? And in fact, it turns out that there are classes of complexity. Different problems are harder to solve. We have problems that are in a class called P, which are problems that can be solvable in a polynomial time by a Turing machine. What does that mean? It means that there is a polynomial expression for the number of steps that has to be done in order for this type of problem to be solved. But there are other problems that are harder. MP is a class of problems that are solvable in polynomial time by non-deterministic Turing machines. Of course, there's no non-deterministic Turing machines. It's just a hypothetical model. You can effectively think of MP classes of problems as being ones that have a non-polynomial time to solve that problem. It gets worse. There are problems that are NP complete, which essentially means that this problem is a representative of a class of NP problems. If you can solve this problem, you could solve all the NP problems. And then there are problems that are NP hard, which are harder NP problems. And a classic example of an NP hard problem is what's called the traveling salesman problem. It is an outstanding question in computer science as to whether the class of P is equal to the class of NP. If it is, then you can solve NP problems in polynomial time. but it's probably not. They're probably not equal, which means there are these distinguishing classes of problems. So why do I care? Well, because complexity is about what happens when problems get large. If you look at the way that we talk about complexity theory, it's with respect to what happens when the problems get larger in size, typically. So the algorithm complexity you can look at, sure, as the number of steps that you have to do, but you can also talk about what those steps are. A sequential step is where you can only do one operation at a particular step. And we can talk about a sequential algorithm as only doing one operation at any step. Everything's sequential. But algorithms can actually run in parallel in the sense that a step may have multiple operations that can be done at that time. And in this essentially means that there's no dependencies between those operations. They're all available to be done, and they can be done now at this step. So this helps running things in parallel because it reduces the number of steps. But the fact is that it doesn't change the complexity class. We still have these complexity classes. So what's interesting here is that we can talk about complexity and parallelism, but parallelism only relates to what we can do with respect to doing things in parallel. And so when we think about an algorithm, we can think that way. You know, what can I do at this step in parallel? We could call that a parallel profile if that helps. But in reality, what matters are the dependencies between operations in the algorithms as we're trying to solve them. So I'll give you an example. So we can consider adding numbers. I want to add a number of numbers in, and I'm going to do it sequentially. In this case, I'll just add one number to the current sum at a time, as you see here. There you go. So that's a sequential algorithm. Can we parallelize this? Sure. How do we do that? Well, we do it by constructing a binary tree of partial sums, as you see here. At the beginning, you know, we have n numbers, and so every pair we can add together, and we get a result, and then we do that as we go down this binary tree of partial sums. So what's interesting about this is that, yes, there's inherent parallelism in this algorithm. There are operations that can be done at the same step in parallel, but you also see that there is a change in the degree of parallelism as the computation proceeds. Okay, here we have n over 2-way parallelism, then it's n over 4, then it's n over 8. And so parallelism as a property of an algorithm is going to change as you continue to perform the algorithm. We can talk about this in a different way to get a sense of how well parallelism is going to affect the performance that we see. And we do so using speed-up models, where we think about the algorithm being sped up by parallelism, and how do we think about that model, you know, helps us to get some handle on how well, you know, a particular parallelism approach might be effective. We have two types of laws. I'm not going to really go into significant detail about them. They are very sort of abstract in the sense that they don't necessarily reflect reality, but they let us talk about certain things. In particular, you know, when we look at an algorithm and we think about parallelism, what is the parallelism degree that's inherent within the problem that's being solved by this algorithm? And so that typically gets related to the size of the problem. You saw that on the previous slide. You know, if I have 1,000 numbers, that's one thing. If I have 1 million number, that's something different. If I have 1 billion numbers, that's even something different, right? In the case of Amdahl's law, we don't let the problem size change as we increase the amount of parallelism within the calculation. In this particular law, we do. You know, And so they end up having different speed up behaviors. Now, why do I really care about this? Because I care about performance. Complexity is about how hard a problem is. It doesn't say anything about how the algorithm will perform on a real machine. Parallelism offers speed up opportunities. That's great. But what is the performance? What are the computational requirements that are necessary in a real computer system in order to execute a program with a particular algorithm? What are the computational requirements? That is, what does this algorithm need to do? And then there's the computing resources, the computational resources upon which that algorithm is going to run. Performance is a measure of how well these requirements are met by the resources. We evaluate performance to understand the relationship between those requirements and the resources that we are using. When I say resources, I mean actual computer system resources. How do we quantify performance? We quantify those by understanding what the computational requirements are, and then trying to take metrics and rates that relate to, how fast, what the operations are that are being performed, and how fast they're being performed, so that we can talk about performance. Oftentimes, we look at a computer system and we can ask ourselves, given the resources that you have, what is the best I could do? And we call that peak performance. It's what the machine is capable of. But the achieved performance is really dependent on how well, computational requirements of a particular algorithm in the form of a program are being met by those resources. Remembering, and the thing you should remember, is that the algorithm itself has inherent parallelism properties. It has a profile. It has a parallelism profile. So you cannot really expect to achieve peak performance all the time, because you might not have enough parallelism in your program in order to be able to do that. Okay, so what does this all have to do with supercomputing? Well, computational power, the thing that we want to understand and evaluate here, has to be what in the context of a real computer system. And when we talk about high performance computer systems, we're talking about machines, computer systems that are using state-of-the-art technologies, including the software, hardware and software, in order to achieve some high computing potential. A supercomputing is a HPC system. It is an HP system, but with the goal that it's trying to achieve the highest performance possible for this particular machine. What's driving HPC and supercomputing? It's all, I would say, in a nutshell, it's all about parallelism. It's all about parallelism. What's the available parallelism? And how well can I actually process that parallelism on a real supercomputing system? How do we understand this? How do we quantify computational potential and evaluate it on real computer systems? Well, here's a history of supercomputing architectures. And it's all about parallelism. So even though we started off in the 1950s with sequential instruction execution, everything else, I would argue, everything else has to do with can we find parallelism? And parallelism here with respect to architecture is how do we modify the architecture such that it has available resources to handle parallelism. Where do we find parallelism? We can find it in the instruction. We can find it in the data, vector processors, in the data. We organize the architectures in such that we could try to continue to increase the available resources, parallel resources that we have for processing instruction level parallelism, data parallelism, and then also look to see how we can scale the system, grow the system, add more resources to it, so that when we have the available parallelism, we can consume those resources, we can grow our problems, we can really take advantage of it. And then we do that turn the crank and we do it with the next generation of parallel architecture and the next generation of technologies that are available to us. So architecture advances, technology advances, and the combination of the two gives us an ability to really build supercomputing systems. Okay. Well, we're not done yet. So when we think about parallelism, sure, we want to have a parallel program, has inherent parallelism in it. It wants to try to take advantage of the HPC resources and so forth. But how do we think about it as something itself that can scale in terms of the degree of parallelism that it's using within the computation? We typically think about that with respect to how we grow the computational work that this particular algorithm in this program is going to form, what is that it's going to work on. We do that, we think about it with respect to peak, for sure, that's okay, but also with respect to the different relative performance as that program scales. And we use some measures of efficiencies to understand that. In our area, we have done this by looking at benchmarks. And the most important benchmark that we've applied over many years, since 1973 or something like this, is the LINPACK benchmark. It's a solving of a dense linear system of equations. The way that this benchmark works is that you tell it how many, the dimensions of the number of equations that you have. That's the scaling factor, right? And then you ask it to solve that problem, and you measure the performance. And what this benchmark does in terms of evaluation is that it tries to determine what is the maximum amount of performance that you can achieve by growing the problem. And so our max becomes the maximum performance in terms of floating point operations per second. In max is the size of the problem. So I grow the size of the problem here until I can't get any more performance in terms of floating point operations per second. And this has been reported every 2 years. And what we see is something like this, where over the history of this use of this benchmark in the supercomputing industry, we get an ever increasing amount of performance out of the number one supercomputing system, which is in red, the number 500 best supercomputing system, which is in this orange color, and then the total, as you see here, among all of those machines. Now, this is a scale here, as you can see, that is increasing in capability as well as delivered performance of supercomputing systems over time. And we have exceeded what's called an exaflop, 2 to the 18th floating point operations per second by the machine here, which I'll show you now. On the top 10, these are the top 10 most powerful supercomputing systems in the world in existence now. And the number one is this machine called El Capitan. And what you see here is this is Rmax. This is the performance rating. And you also see something, in this case, about the architecture of that machine. It has 11 million plus cores, available computer cores to execute instructions. There's several things that are interesting about this. One of the things that you might look at, it has to do with the power that this machine is drawing. This is the peak amount of performance that machine has available to it. And then this is also the size of a linear system in terms of dimensions that it solved in order to achieve this peak performance. Like I said, there's interesting things to look at here, but this is just trying to give you a sense as to how capable these machines are. But there's also something that's a bit subtle here. And it has to do with what are supercomputing systems being used for. To a large extent, the history has been for modeling and simulation, what we would call ModSim. Simulation of physical systems, theoretical systems, and so forth across a whole variety of different domains. And the core computations that happen within these simulations are ones that are a variety of different types of computations. Some of them, probably more with respect to current use of supercomputing systems, have to do with the solving of 3D partial differential equations using calculations on sparse matrices, not dense matrices, like LINPACK. You think then as to whether HPL, high performance LINPACK, is still relevant. Maybe, but the fact is that technology and HPC architecture have changed over time, where arithmetic calculations that were expensive are now less so. Data movement is becoming much more of an important factor. And in this reality, for those dominant types of calculations that are being performed in these applications, Jack Dungara says LINPACK is no longer strongly correlated to real scientific applications. I'll tell you who Jack Dungara is here in a second. So they devised a different benchmark based upon high performance conjugate gradient. It is still solving AX equal B, but now A is very large and sparse, reflecting the types of computations and the way that you structure the problems that are having to do with the discretization and the types of structuring, partitioning of partial differential equations. Here's the problem. Here's the rub. That if you look at the HPCG benchmark and you compare it to HPL, here's HPL. Here's HPL. Here's HPCG. This is the percentage of the peak. This is the percentage of HPL that is being achieved by this HPCG benchmark. It's less than in the max here, they're 3.6%, more like 1%. This is a problem. This is a performance. This is a problem. It's not necessarily a performance problem, but what it reflects is the fact that different applications have different performance. This is to be expected because different applications have different parallel performance behaviors. Okay, and in the case of HPCG, it's a lot more determinant by how well you manage the data within this application than it is the arithmetic calculations. But you should be concerned about this because here I have the top 10 supercomputing systems in the world, right? And compared, ranked by HPL results. But I'm only getting less than 4%, and in most cases 1% of the performance that these machines are telling me that they can get with this HPL benchmark. That's a real concern. And so, when we look at trying to evaluate performance within HPC systems, we are witnessing a variety of things happening. There is a changing in the architecture. There's a changing in the technology. There's a change in the applications. And so this is reflected in looking at what's actually available, what is being used in these HPC systems now. It's mostly commodity processors and accelerators and interconnection networks, and practically all of them are running the Linux operating system, right? What's happening within HPC technologies is from a point of view of processors, is that there's now more and more concern about what's called the end of Moore's law. But what I'm interested in is, performance evaluation. I'm interested in parallel performance. It is a part of a software ecosystem. And if you look at the types of systems, this evolution, as you see here with this red arrow over time, those are the architectures. It's not just about the architectures and the machine technology. It's also about the software. So Jack Dungara, I mentioned before, is a 2021 ACM Turing Award winner. And his talk at the Supercomputing conference was on a not so simple matter of software. Software is what is driving the ability to use these advanced architectures and technologies. There's hardware evolution that's happening, the parallel software that we need to develop, parallel programming, the numerical libraries, the communications libraries, those need to advance too in order to provide access to the capabilities that these machines are offering us, right? So I argue that performance technology as well must react to these new requirements in terms of measurement and analysis capability. So let's talk about parallel performance. I would say that it's not so simple matter of performance. It's that I'm interested in my research in parallel performance. And in fact, from a even fundamental point of view is that what is the performance of a parallel computation on an HPC system? How do we understand that? How do we understand performance? I think of it as a knowledge-based process in the sense that I have to have some way to observe performance. I have to, based upon that information, try to identify what's going on. What is the performance behavior that I see? And how do I explain when I have good performance or bad performance? And if I can do so, then I can actually use that knowledge as a way to tune performance and get more optimal operation. It's this process that intrigues me for the most part. How do I make it more effective and productive? There are methods for performance problem solving, right? We need to do this. How do we do it? How do we build technology in order to be able to learn about performance, analyze it, and to feed it back into that software ecosystem, so that we can improve it. And so I've been studying this even since my Ph.D. work. I can't seem to get away from my Ph.D. cases. And this has to do with thinking about parallel computation performance from a point of view of how do I observe it? How can I could just do like they do in WinPack, just measure the time from the beginning to the end. That doesn't tell me anything. But I need to observe more in order to understand. But when I do so, I intrude on the performance. And in some cases, I even perturb the performance, which is not good. And so I came up with this measurement uncertainty principle. As you try to observe more, you might intrude more and it could possibly perturb. And it might even be such that your perturbation is causing execution behaviors that would not really exist if you were trying to observe it all. So this is a real issue, is that what is the accuracy of performance analysis when I don't really know what the true performance is? I might know something about it, but if I need to know more and try to rationalize about it, I need to do something else. I need to try to implement some technologies that allow me, to at each one of these stages here, learn something, starting from observation. This is just showing you a graphic of where we've done our research, try to apply our research, and in what form. From performance observation, we looked at how do we instrument programs, how do we make visible certain properties, there are certain events that are happening, measure them, analyze, visualize. But once we have that data, then how do I understand what's happening when I do things like scale a problem and so forth? So we have to run multiple experiments. We build technology for experiment management and performance data storage. How do we diagnose? We'll apply data mining and other things, even expert systems and so forth. and then performance tuning, which is a fairly hard problem. So this is what we've done. Since I've been at Oregon and starting in 1991, we've tried to look at these problems over 34 years now or so, and I just sort of give some labels to what I think we were doing at the time. So focusing on observability, it's not like these are done after you finish this period of time. Focus on diagnosis, look at issues of complexities having to do with scaling and so forth. And this most recent ones I call productivity, is that as we have more complexity within the HPC system, we need to integrate what we do in our performance areas with those other software tools, right, and the hardware in order to manage that complexity in a more productive way. And the project that we've had going on for all that time is the Tau performance system. The Tau project that we started and has been going on since 1991. And we had two goals at the very beginning. One is to try to come up with a way to think about performance problem solving framework in the form of current as well as future HPC systems, what they look like, what things we should be thinking about. This picture here is dates back, I think, to probably 1994. And then also build technology. How do we create a tool suite that supports this model of what where we're going to be doing performance problem solving and the capabilities that tool suite might have. This is a project history. I just want to show you a few people going sort of over this period of time in these different phases. I'm not expecting you to look at any of this detail, but it sort of identifies some of the problems that we were working on at the time. Bert Moore, who's a famous guy now at Research Center Jülich, Samir Shinde, Kevin Huck, Camille Cote, and one of my most recent Ph.D. students, Srinivasan Ramesh. So what does Tau look like in a nutshell? It does a whole bunch of things. And we've tried to make Tau work on every parallel computing system that you could imagine. So it's highly portable. It supports these different parts of the tool suite. And again, I don't expect you to know anything about these things necessarily, but it just shows you a bit of what it is that we've tried to do. It's an interesting research area just because things are always changing. And that's what kind of keeps us energized as looking at the next problem to solve. More recently, we've tried to address certain research issues that are coming again from the HPC community as things are evolving. For instance, most recent HPC systems, supercomputing systems, are built upon heterogeneous system components. That is the combination of CPU and GPU processors, as well as other components within the HPC system that like having to do with network interconnects and so forth. And these heterogeneous systems need to be programmed. And so there is software technology, compiler technology, programming languages, and so forth that are going towards programming these types of systems for performance portability. Well, as those exist, as those get implemented and get applied, we need to have tools that work with them to support heterogeneous computation. There's a lot of interest in task-based applications that operate as multiple tasks, sometimes many tasks that are executing at the same time, working together. This particularly gets hard when those tasks are asynchronous. And when that asynchronicity was introduced into HPC systems, that caused a problem for us in Tau because we didn't have any support for asynchronous. So adding that into Tau was something that we worked on. We have been many times working with compiler technologies to support instrumentation of programs I've always had some interest in monitoring. And so looking at next generation applications, I'm interested in how we support performance measurement and analysis while an application is running. So I've been looking at workflow systems and building some type of monitoring support for workflow systems. Samir has been very involved in looking at the Exascale scientific software stack, which was a product that came out of the ECP that I'll tell you about here in the next slide, and so forth. So all of these are being driven, as I said before, not only by the systems, the HPC systems, but also by the applications themselves. There was a last 7 or 8 years, a project in the United States that some of you probably know about called the Exascale Computing Project. And this was intending to try to build applications that would be ready for exascale computations, exascale machines, okay? And to create the necessary sort of ecosystem to support those applications in terms of programming models and the runtimes they're built upon. Tools, this star means this, we were supported off of this column here, trying to extend math libraries and other tools like data visualization and so forth in support of the necessary things that need to be done in the context of an exascale computing system. And this shows you some of the timeline as to what those systems were in the Department of Energy in the US, pre-exascale systems, as well as the ones that are delivered that you saw on the top 500 chart. And Tau runs on all of these platforms presently. Hopefully it continues to run on those platforms. So I wanted to take the last moment here to talk about the future. And the future is, in some sense, like the past. There'll be continued dynamics within the HPC field, as technology advances, and the types of problems that we would like to solve are going to require next generation platforms, exascale machines in particular, but there still is this concern for Moore's law. And there is a paper that you see here referenced. So there's plenty of room at the top, what will drive computer performance after Moore's law, that tried to argue that there's plenty of ways to continue to get performance out of these HPC class system supercomputing systems. There are continued large-scale HPC systems proposed, being built and proposed. Jupiter is a good example. About a month ago, early September, it became the first European exascale class computer system installed at Research Center Jülich. But there's looking out to even something much larger. This Fugaku Next machine, a zettascale, 1,000 times more powerful than our exascale systems of today. Clearly, what's going on is in the supercomputing, high-performance computing, and supercomputing world is the influence of AI. And AI is affecting both modeling and simulation, as well as what's called AI-coupled workflows. The idea is that I have HPC systems, maybe with traditional ModSim, but trying to integrate AI into the computation, into the application, and in the form of a variety of things. One of them is to use surrogate models, replacing the actual computational model, ModSim-based traditional computation, with some type of AI surrogate. But maybe in the sense of constructing applications that has the AI built in, where you're learning on the fly and you're trying to incorporate the AI from what you're seeing within that simulation. So why? Why is that important? It's because the AI model, if you can train the AI model, it will perform faster. In the actual ModSim simulation, it will perform faster. It is faster. It just ideally, hopefully, is accurate enough to be able to replace the actual computational part. But there's more than that that's happening. there is the development of foundation models that are going to be important for scientific computation. But those foundation models are also important for other purposes. And this gives you a sense as to what else is happening within the HPC and supercomputing marketplace, if you will. So these are traditional companies that have been producing supercomputing systems over the many years. And this is from 2025 in September, showing the size of the market for these companies in the more traditional supercomputing area. But there's also companies, as you see here, that are in areas having to do with, a variety, things like social networking and computing and data centers and so forth. And they have a much significantly larger presence within the marketplace. And recently, within the last 2 or 3 years, this has also been influenced, by AI. And as you see here, in the case of NVIDIA, as a company that provides computing components, GPUs in particular, to businesses that are going to be using those as part of the fuel for AI computing. What does that look like? Is the idea of AI training and inference driving problems, in the world to where they want to apply AI training and inference, right? But also driving the need for HPC technology. And these are becoming in the form of frontier foundation and frontier models that are consuming significant amounts of computation within the applications of creating those models and the applications of those models, like significant. So where's the HPC computing technology going? It's going here. It's going to AI computing out in the world. Now this is beyond traditional HPC. You can see what the amount of computation is to a large degree. These applications are consuming huge amounts of computational and data resources for those computations. In terms of power, they're consuming huge amounts of power. They're also hugely being invested in. Compared to what the investments are in the traditional HPC, as we think about it, from our community, you see the amounts of money that has gone into the latest top supercomputing systems and the amount of power. Okay, that's a lot, for sure, that's a lot, right? But compare that to XAI Colossus. That machine is going to be a $4 billion machine with 10 times the amount of power. So the takeaway here that I want to kind of leave you with is that there's a lot of excitement happening, in HPC area supercomputing, today, but it's all about parallelism and performance. And this has a fundamental background in computer science and history. And there's interesting problems with respect to parallelism and performance. Supercomputing is and always will be, about scale. What drives it are the current problems that we want to solve, but it's also business markets, as we see today. We have real concerns with respect to supercomputing having to do with efficiency. This is not only performance efficiency, like I was contrasting between a LINPACK type of computation and a conjugate gradient type of computation. How much of the performance how much of the capability of the system can we actually use? It's an efficiency issue about performance, but power is becoming more and more and more of a problem. It is interesting to think that AI might be, one of the things that is causing this problem, but it's also interesting to think that it might be that AI will help to address these problems. And how many of you know Yogi Berra? He's a famous an American baseball coach. And what he's also famous for, these little quotes that he has. So when we think about the future is not what it used to be. Is one of the more funnier ones. I'm going to stop here. I don't know where my time is, but hopefully I didn't go over too long, and maybe take some questions from you all.
Thank you very much.
Thank you.
Yeah, this time is perfect. We still have 2 minutes or so.